Hi, my name is Ryan Lynch, and I am a staff scientist at the Bank Observatory and a member of the NANOGrav Searching Working Group. And I'm going to talk to you briefly today about searching for pulsars and how that fits into NANOGrav's mission. So why do we look for new pulsars in the first place? We know of about 2,000 pulsars so far, so how many more do we really need? Well, we've only discovered about 5% of the pulsars in our galaxy, so there's still a lot out there left to find. And adding more pulsars is one of the best ways that we can improve NANOGrav's sensitivity to gravitational waves. In fact, NANOGrav's sensitivity increases proportionally to the number of pulsars that we add to the array. And outside of gravitational wave detection, we find cool new pulsars every time we look. Every new pulsar survey that we perform ends up finding a lot of really fascinating new systems because pulsar surveys are sensitivity limited. So every time that we search for new pulsars with more sensitive telescopes, more sensitive instruments, or in regions of parameter space that we haven't looked at before, we find really interesting new things. There are a lot of challenges to finding new pulsars, however, that we have to overcome. One of the biggest is the effects of man-made radio frequency interference, or RFI. RFI can make it a lot harder to find pulsars because sometimes it'll masquerade as a pulsar, or it'll interfere with the very weak signals that we're trying to detect. Also, sensitivity to the fastest millisecond pulsars that we're interested in for NANOGrav requires very fast sampling. Modern surveys typically use sampling less than 80 microseconds, which means that we're collecting power from the telescope once every 80 microseconds or less. And this is over many hundreds or thousands of individual frequency channels. We have to use lots of frequency channels because we have to mitigate the effects of the interstellar medium. There are two main effects that we're worried about when searching for pulsars. One is known as dispersion. This is a frequency-dependent delay in the arrival time of a pulse at the telescope. You can see that on the left panel of this image. The high-frequency pulses actually arrive at the telescope first, followed by pulses at lower radio frequencies. Now in this image, we're showing one rotational phase of the pulsar, and you can see that the pulses actually arrive more than one rotational phase later at lower frequencies than at higher frequencies. So the pulses are actually wrapping in rotational phase. When we search for pulsars, we add power at many different radio frequencies up together and then search for periodic emission. And if we were to do that for an undispersed signal, the actual periodic pulse would be completely washed out. So we have to first correct for this dispersive delay before we create our time series and search it. If we correct for it, then we can recover the pulse that's seen in the bottom left of the left-hand panel. Even then, though, there's still some leftover dispersive smearing within a finite frequency channel, just due to the difference in the arrival time between the top and the bottom of a very small frequency channel. And at low radio frequencies, where this effect is more severe, that can really impede our ability to detect very fast pulsars. So we have to use smaller channels in order to minimize that dispersive smearing. We also don't know what this dispersive delay is going to be ahead of time. It depends on a quantity called the dispersion measure, which is the integrated density of electrons in the galaxy between us and the pulsar. Since we don't know that value ahead of time, it's an extra parameter that we have to search over. And in practice, we usually search over many tens of thousands of trial dispersion measures in order to find just one pulsar in a particular point on the sky. The other effect that we have to worry about is scattering. This is due to a change in path length from scattering in the interstellar medium. So some pulses go straight to the Earth, while others are deflected and take a longer path, and therefore arrive later. This effect is strongly frequency dependent, as you can see in the right-hand panel. At 1408 megahertz, there's very little scattering evident, and you can see the intrinsic shape of the pulse very, very well. By the time that we get down to a few hundred megahertz, we see this very long scattering tail, which is characteristic of this effect. And as it spreads power over many individual time samples, and decreases the amplitude of the pulse, it makes it harder to detect faint pulsars. So to mitigate this effect requires thousands of radio frequency channels and dispersion at tens of thousands of trial dispersion measures. Once we do that, we have to actually search for the pulsars themselves. And to find binary systems, we have to perform acceleration searches. These take into account that there's a Doppler shift in the apparent period of the pulsar, which causes that period to seem like it's changing throughout the course of an observation. That spreads power out over many Fourier transform bins, which we use to search for pulsars, and we have to account for that if we're going to find pulsars in short orbital period binaries. A lot of the pulsars that we time for NANOGrav are binary pulsars, so this is very important. But it's also computationally very intensive. We also have very large data volumes. It's not at all uncommon for data rates of several gigabytes per minute in large area pulsar surveys, and we're collecting many, many hundreds of hours of data, if not thousands of hours. So the total volume for a large area search for pulsars may be in the order of petabytes. And we produce millions of candidate pulsars, many of which are going to be man-made interference or spurious signals. So we have to intelligently inspect those candidates in order to find the real pulsars. So here are the steps that we actually take to finding pulsars. First, we have to write a good proposal and get some telescope time. We tend to use a lot of telescope time for large area pulsar surveys, so it has to be a pretty good proposal. We record lots of data. We remove RFI as best as we can. We de-disperse the data to produce what we call de-dispersed time series. Then we take a Fourier transform of that time series, and the Fourier transform is a technique for finding periodic signals. We have to search for those Fourier transforms for periodic signals using this acceleration search technique. There's also some new techniques that are becoming popular that are called fast folding algorithms. This technique has actually been around for a while, but it's very computationally intensive and hasn't usually been used. But this searches for periodic signals in the time domain, and it may be a better way of searching for longer period pulsars. We also search for single pulses from sources like rotating radio transients and fast radio bursts. We identify the best candidates, and then we have to go back to the telescope, reobserve them to prove that they're actually real. So there are several important surveys for NANOGrav that are going on right now. One is the Green Bank North Celestial Cap Pulsar Survey, which is being carried out using the Green Bank telescope, which you can see down in the left corner of the screen there. This is a lower frequency survey at 350 megahertz, covering the entire sky visible to GBT. It's found several good millisecond pulsars that are now included in NANOGrav, and it should be wrapping up over the next few years, and we expect we'll find a few more. There's also the Pulsar Arecibo L-band feed array survey using the Arecibo telescope. We call it P-alpha for short. Arecibo you can see down in the right-hand corner of the screen. This is being carried out at a higher radio frequency and is specifically targeting regions near the galactic plane where we tend to find a lot of pulsars. P-alpha has also found a lot of really fascinating pulsars, including pulsars that are included in NANOGrav, and the first, so far only, repeating fast radio burst. There's also the Arecibo 327 MHz drift scan survey. This is a low-frequency survey being carried out with Arecibo, and in this survey, the telescope is actually parked at a particular position, and the sky is allowed to simply drift through the telescope beam. There's also follow-up of bright Fermi sources. Fermi is a gamma ray telescope, and it turns out the millisecond pulsars tend to be very bright in gamma rays. So you can go and look at unidentified Fermi point sources that look like they might be pulsars with a radio telescope like the GBT or Arecibo to search for a radio counterpart. And we found dozens of millisecond pulsars this way, including many that have been included in NANOGrav. NANOGrav is also leading some targeted surveys of interesting parts of the sky. And interesting in this context means parts of the sky where we currently don't have a whole lot of pulsars included in NANOGrav, for which we need to kind of fill out the sky sensitivity of the array, as well as towards regions of the sky, such as the Virgo cluster, where we might be able to find a strong gravitational wave source, like a massive black hole binary that's relatively nearby. And to detect a source like that, it helps to have a pulsar that you're timing in that region of the sky. So all of these projects include members of the NANOGrav Search Working Group. Many of them are also parts of larger collaborations. And it's relatively easy for students and undergraduates to get involved in pulsar searching through these different projects. Like I said earlier, we produce quite a large number of candidate pulsars, and it takes someone to go through and look at the best candidates and to decide if they're real. So we usually use diagnostic plots like the one I show here, where you can see on the left-hand panel these dark lines that correspond to pulsed emission in a particular rotational phase of the pulsar showing up throughout the course of an observation. You can see an integrated pulse profile at the top. You can also see in the middle the pulsed emission across a wide range of radio frequencies and some other diagnostic plots and information. So these are the types of things that we need to look at with a human eye after we've already applied some intelligent algorithms like artificial intelligence programs and candidate ranking algorithms to try and pick out the best pulsars. So if you're interested, I strongly encourage you to get involved in pulsar searching as part of NANOGrav. Thank you.